All right, in these next two videos, I want to actually talk a little bit about how we're going to analyze the effects of a multiple group experiment. But before we do this, we're going to address a couple of more fundamental points. So the first one I want to remind you of from last class's lecture is, remember what I told you is that all of statistics that we're going to learn comes down to three basic terms or ideas, which is observation, expectation, and deviation. What I mentioned before is expectation can be thought of as the means. I'm going to explain why this is the case in just a moment. Okay. Observations you can think of as the individual scores. Okay. And then deviations, and it turns out sometimes these observations can take the form of a mean, but we'll come back. I want you to think about them as scores right now. In other words, what do we observe people actually scoring? What do we expect them to score? And I'll explain in a moment why we're going to use the mean for that. And then deviations is what's the difference between these two? In other words, observation minus expectation equals deviation. Okay. So let me say a little bit more about why that's the case. Let's imagine a game for a moment. Let's imagine that let's take our I was going to say Bill Gates because Bill Gates has long been one of the world's wealthiest people, but thanks to his philanthropy, he has actually given away enough money that he has now, I think, become America's second most wealthy individual. And actually, let's still take Bill Gates because he's more likely to do this kind of a generous experiment. So let's say Bill Gates looks around at this classroom and says, here's a bunch of struggling students. I want to help them out. So here's what I'm going to do. I got lots of billions of dollars. Maybe I'll take $1 billion and I'm going to give it to someone. I'm going to give it to the person who guesses the number that I have in my mind. Now, you say, well, what number is in your mind? He said, well, here's the deal. The number is between 0 and 100. You say, well, there's only a 1% chance of guessing that. So Bill Gates says, okay, you're right. How about this? I will give you a portion of my money for however close you guess. So for instance, if my number is 72 and you guess 73, you get 99% of $1 billion. You get $990 million. If my number is 72 and you guess 84, which is 12 away, you get 88%, and so on and so forth. If you're very far away from my number that I'm guessing, then you get less of my money. The question is, if he is truly choosing a number at random, what number should you guess? You should guess 50. 50 is the average of all the scores, of all the possible scores in there. It's the mean. Why would you guess 50? Well, if you guess 50, you are likely to minimize how far away you are from any other number that Bill Gates might guess. In other words, by guessing that mean or that average, you minimize your error, the difference between your guess of the mean or the average and whatever random number Bill Gates has in his mind. Okay, if the number could truly be all these, then 50 is going to be your best guess because across all the possible different numbers, 50 comes the closest to all of them. Let's say Bill Gates changes a little bit. He says, well, how about this? Now I want you to guess the height of the person in this class whose name I draw at random. So you look around and you have a class full of people. And if this class is like any kind of normal class, if it's big enough, what we should see is we should see a normal distribution of heights with one or two very tall people, one or two very short people, and a lot of people in the middle. If he says, the closer you come to guessing their height, the more money I give you, what do you guess for their height? What you'd want to guess is the class average. In other words, you expect the average person in the class to have an average height. This is your expectation when all else is equal. When you don't know which of these people he's going to choose, it's best to choose the number that exactly splits the difference between all these. In other words, the one that leads to the smallest deviations between your guess and the observed score. So the difference between your expectation and your observation is your deviation. Okay, so I want to have that in the background of our minds, because here's the thing, not all people are alike. They're not all alike on intelligence, on height, as we saw here in this set of scores, on happiness, on anxiety. People differ. Or, in other words, people vary. There is variability in scores. So I'm going to erase this. You can always rewind the video if you want to come back and see us. So let me erase some of this right here. But let's keep observation, expectation, and deviation up there. So let's talk about variability, because it turns out that variability is at the heart of statistics. Variability simply means, in our circumstance, we're talking about experiments, people are different. And they're different on our dependent variable, whatever it is that we're measuring. Anger, happiness, height, hunger, whatever it is. So here's the next question I want you to think about. Why would people within a treatment group vary from one another? So we're going to talk in just a moment about what causes within groups variability. Why would people who get the exact same treatment, maybe they all get, in our last example, maybe they all get drug A, why would they vary on happiness? Because they're all getting the same drug. Next, let's imagine we compare those who got drug A and those who got drug B, or maybe even more simply, our control or placebo. Why would these two groups differ from each other in happiness? What causes between group variability? Okay, well, what I want you to remember, these are the two key facts about variability. Then I'm going to illustrate it in an example. We'll stop this video and we'll do one last video at the end. So within groups variability, we think about in statistics as a pure measure of error. What causes this within groups variability? Lots of stuff. People's genetics, people's background, people's attitudes, people's experiences that morning, random chance, the breeze floating through the back of the room as opposed to the front of the room may cause someone to be distracted. Lots of things cause it. What we call all of those things, background, genetics, breezes, happenstance, we call it error. An error simply means those variables that we don't control or measure. If we measure it, it turns out we can factor it out. So within groups variability, these differences that exist within a treatment group are our measure of error. This tells us how much are people just differing from each other in general. Between groups variability also gets affected by the same kind of error, because you may have a few more genetically tall people in one group, or people who have higher levels of extroversion. In other words, they're more genetically predisposed to be happy than others. So there's still going to be some error that makes groups differ, but possibly, and if we're conducting an experiment, hopefully also our treatment. So one of the things that would cause two groups to differ from each other on happiness, so if this is our control in our drug A group, one of the things hopefully that causes this drug A group to differ from our control group is the drug that they're receiving, our treatment. So let me give you an example, let me illustrate, and then we'll end this video. So let's imagine that a teacher has changed some element of their class, and they want to know how effective that change was in increasing their students' learning. So what they want to do is compare the scores of two classes on the same exam. And this actually comes from data provided for a teacher when I help them to try to look at these differences. First, they plot all the scores from their first year, 2006, on a frequency histogram, like this. This shows us how many people, this is the number of people, how many people scored each one of these scores. For instance, it appears that 4 people scored a perfect score on this test. Now, they collect the same kind of data for the next class, the class of 2007. What I want you to notice is it looks somewhat similar with just a few key differences. So I want you to take a look at this. Just by looking at the data, which of these classes do you suspect did better on average? 2006 or 2007? Pause the video and make your conclusion. Okay, if you said 2007, you are correct. Why would you say that? Well, oftentimes because we take a look up here and it looks like we have a few more perfect scores, we have a few more of these higher scores up here, and 2006 looks like they have a few more of these low scores down low, right? So it appears that there's a difference here. To represent these differences, what we do is we calculate the mean scores of each group. So for 2006, we take the average score, which is 49.09. This is if we were to draw one single student from this class and try to guess what their score is going to be, we would guess this mean. This is what we would expect a 2006 student to score. In 2007, we do the same thing, and we find that the average is 53.48. So if we know nothing else except for the means of the two classes, does it look like our new teaching method worked better? Yeah, there at least appears to be a difference between these two means. But the question is this difference statistically significant? If yes, why? If no, why not? How would you know, and what might variance or variability say about the differences between these two scores and their significance levels? Okay, well, let's take another look. One reason why we can't conclude with certainty that these two groups are different is because each of these means does not perfectly represent individual scores. So let's take a look at one class in particular. Let's look at 2006. Just as we saw with the scatter plot and regression lines in other classes that we've done, our means don't perfectly represent every single person. Instead, the mean either overestimates or in some cases, vastly overestimates or underestimates each individual score. So here what we see is a deviation between our observed, the actual scores, and what we expect that student. And this happens with every mean. There's always variability between observed scores and our expectation, or the mean of that group. Over the long run, this error adds up, as you can see. The more these errors, or the more within group variance there is, the less confident we are that our mean is actually the true mean. And the more likely it is that this mean score was kind of influenced by random chance. Like here, we have one person who scored super low, so this person might have pulled our mean down from what it otherwise would have been if this person was out of the class. Okay, in the next video, I'm going to overwhelm you for a second with a page full of statistics. In fact, just to inoculate you, let me show you this page just to end this video. I'm going to show you this, let your mind cloud over a little bit, and in the final video, we're going to come back and actually talk through these statistics and hopefully make sense of what they are and of how this helps us to better understand how individual differences or variability can affect how well we see differences between groups.